This is the Real Digital Transformation podcast series, empowering technology and business professionals to succeed with digital transformation. Now, here's your host, best-selling author and series editor of the Pearson Digital Enterprise series, Thomas Earl.
Hi, this is Thomas Earl, and welcome to another edition of the Real Digital Transformation podcast series. Today I have with me the CEO of InfluxData, Evan Kaplan, who will be talking to us about the relationship between database design and architecture and physical AI. Specifically, how physical AI cannot be realized without some specific attention we need to give to the database layer. Should be interesting. Welcome, Evan.
Thanks for having me. I appreciate it.
So let's get right into it. Most of us understand where we're heading with physical AI, the relationship between physical AI and agentic AI. But it's interesting now to think about how this impacts the database layer in our solution architecture or within our greater enterprise architecture. So for those involved in establishing and maintaining that dimension of the overall architecture, what are your thoughts? What do you see as being necessary for us to design, to configure, and how does a shift toward physical AI impact the database architecture specifically?
Yeah, that's a great question. Maybe let me frame a little bit some of my thinking on the topic. I think most of what we talk about in the AI world has been, at least for the last 3 years, has been around generative AI, right? It's been about the capture of the digital corpus that exists out there today and gets scraped every single day. And if you listen to the narrative on the generative side, it's that we actually have a shortage of data. It's that we need to create synthetic data to improve our models to make it better and better because we've scraped basically all of the digital data that is generally available. And so that's where the generative side is. And the generative side's a probabilistic outcome. So when you enter something into ChatGPT, right, most of the stuff you're getting back, most of the model stuff, most of that is probabilistic. In physical AI, you have a different requirement and a different relationship to the data. One is physical generally has to be deterministic, right? And so if you have a robot who's cleaning your house, that robot can't really run over the cat. And if you have a self-driving car, you want the precision level to be pretty tight. So you want it largely deterministic rather than probabilistic. And so how you get determinism or how you get deterministic outcomes is that you get higher and higher resolution pictures of the physical world. And so higher resolution in the world that I live in is collecting tighter and tighter timestamps. And so at a database layer, in some cases, it could mean nanosecond timestamp. It could be milliseconds timestamp. It could be seconds timestamp. But the better and more accurate picture you have of the physical world, the better you can build a deterministic model. So that's the frame for the question. So what does it mean at the database layer is if all of a sudden you're collecting all of these, let's call them timestamp measurements. So, those measurements could be, light, pressure, temperature, speed, heart rate, what have you. If you all of a sudden you're collecting huge amounts of that, you have 4 or 5 problems at the data layer that you would not see in other use cases. One is the ingest level could be very dramatic, billions and billions of points a second. So if you talk about some of our customers who have 10 million devices out there, or 10 million things, all of those things are reporting every second, every half second, whatever. Now you have a huge ingest problem. 2 is you have a huge query problem, because if you need those queries to have relatively low latency, then you need something at the data layer that's capable of, say, sub 10 millisecond queries, sub 20 millisecond queries, things like that at scale. 3 is you're now collecting huge amounts of data that with high resolution that you don't necessarily need to keep around forever. And so you have this issue of you want to downsample the data, right? So you want to summarize it at some appropriate level, which means really big eviction workloads, which you're getting rid of a lot of data and summarizing it. And then 4 is you need to, if you're storing it over long periods of time to build your physical AI models, all of a sudden the price of storage really does matter, particularly if you're collecting high resolution data. And so you take those 4 problems and you sort of have to address those at the database layer. A normal relational database is just not up for the task. So sorry, there's a long-winded answer for you.
Yeah, no. And I think when a lot of architects hear that, they will ask, well, wasn't big data supposed to address problems like that pertaining to the storage, maintenance, consolidation, processing of massive amounts of diverse data? Don't big data platforms solve some or all of those problems? How is it that a shift within the AI world to physical AI necessitates going beyond what big data platforms have traditionally done for us?
Yeah, it's a really good question. And the answer, it's a relatively simple thing to understand, is the way most of these effective, obviously we're coming from a perspective of the time series category. The way these time series work is they're operational databases. And so the idea is that they're operating in pretty close to real time at high levels of, as I mentioned, ingest and query rates and things like that. And when you have the big data model, whether it's the old Hadoop, H-based kind of model, or whether it's the lake houses, which I think are, where everything is going, and you've got, the Spark-based models, those things, just the latency, they're not built for handling operational workloads. They're built for building the models. They're elite at taking the variety of structured and unstructured data and building models, but they're not elite for running operations on it. The latency, there's no edge, they're generally all cloud. There's just a lot of stuff going on there that from an architecture point of view, you end up with real problems if you want to make them operational.
So what is it that the database layer needs to evolve to from the traditional big data platforms, which had various types of distributed storage options, but as you mentioned, are not perhaps capable of meeting the operational demands of physical AI solutions specifically? What is then the next generation? Is it, so we've moved from various individual databases, relational databases, object storage, and so on, big data platforms dealing with larger amounts of diverse data. Do you see this now as a new generation of database technology that we need?
I think it's like many other, I think it's a variety of existing vendors, newer vendors coming to solve what is the present problem. So if you look at what the lake houses have done, they've done a very artful job, particularly Databricks and Snowflake, but also the hyperscaler versions, Redshift, Fabric, and BigQuery, of building this in the cloud service as a broader data platform. So data warehouse and data platform. And those things, for those of you who've been around the database world a long time, they're the Oracle and IBMs of our modern. This is what you choose. They're core to your architectures. They're not going anywhere. They're getting better and better and more capabilities falling into them. But what's also happening is that around that, that situation, you have to have these specialty-oriented databases to handle these workloads. So you don't end up with, well, we used to be the cases, I used Oracle for everything, or I used Postgres for everything. You're not going to end up saying I use Lakehouse for everything. So, you have vector databases that are really ideal for some of this sort of stuff. You've got time series databases, you've got search databases, in some cases you have document databases, and they're relatively easy to deploy and spin up and spin down. So your architectures are really thoughtful combinations of those things. And your long-term backend is likely something that looks like a lakehouse. But the databases that feed it, that create it, that work with the data, that operationalize it are different than the lakehouse.
Mm-hmm.
Does that make sense?
So it's going to be a collection of existing and new database technologies. Is that accurate?
Yes. Yeah. And older vendors are updating to meet the demand, and newer vendors are emerging.
And with physical AI, in terms of the nature of the data it generates, the nature of the data it continually needs access to, and then as part of that, the reasoning logic that drives it also requiring, beyond the physical hardware, the reasoning logic also requiring its own or related data access. Do you see those two as separate aspects to a database architecture, or have you seen in physical AI solutions it being just one collective relating to the hardware mechanics as well as the agentic reasoning logic that needs to process so much of its own data in order to figure out how to deal with situations, overcome obstacles, carry out tasks?
I think these are definitely componentized architectures. The way we think about it, and so, we're biased. We're not biased, but, we have a certain lens, which is, we see the world as a lot of these time series related stuff, a lot of these measurement, these instrumentation, this high telemetry sort of stuff. The way we think about it is at our layer, we think we are the eyes, ears, skin, if you will, of the model, in that we're picking up everything that sensors are saying about the real world. So the sensors are in the real world. We're collecting that data at high pace and all that sort of stuff. We're then making that data available to stuff that is happening in the lakehouse. So you might take our high telemetry data and you might combine it with some video stuff, even some unstructured business stuff and some other stuff to build a thoughtful model in which your agentic AI runs on top of, right?
Mm-hmm.
And then on the other side of the equation, because you want to take action on this model and ideally run control systems, right? You want these systems to run in real time. Then we take action on it because we're running those queries in really fast time. And so those queries drive action. And so we think of ourselves as the hands and the arms, and we think ourselves as the eyes, ears, and skin, the sensors. And where the intelligence gets built and the models get built is the brain, and we're not necessarily the brain. We do what you tell us to do.
Mm-hmm.
Basically, we give you the data and we do what the model tells us to do. That's a great control system model. Low latency, super fast with high intelligence. That's kind of our canonical.
Okay. So to give those who are interested in learning about or who need to prepare for physical AI to be part of their greater ecosystem within an enterprise, do you have some idea? Can you give us some idea? Like if, let's say you have a robot or a droid, mm-hmm. Carry out a simple task, like carrying a box from one room to another room over the course of 3 minutes. How much data would the execution of that task produce, and how much data might the robot need to access to carry out that task?
That's a great. I have almost no way to answer that. It's
Well, is
it's
it a lot or is it a little? In terms of
I
like,
think it's a lot. I
yeah,
think it's a lot. I think to train that robot is a lot. Lots of
right,
micro movements, lots of spaces, lots of things that could vary in the environment, lots of trial and error because it's fundamentally a control system operating in real time. It's lots of data. Now, once the model is trained and it's there and it knows what to do, it's probably less data, but more operational stuff. Like now I have to respond when the cat crosses the road and I have to do all that sort of stuff. It's you're trying to build what is essentially an autonomous system. So it is not going to be lightweight from a data point of view. Under no conditions is going to be lightweight. How much? God, I just don't know.
right. I guess I mean, to be prepared for this, if you're going to introduce this into your business operations, and you're going to have different types of physical devices perform actions for you on a regular basis, every day, every hour, every minute. Are those robots or other devices, are they constantly producing new data as a result of their actions? And does all that data need to be indefinitely stored, or is some of it, can some of it be summarized and the rest discarded? Just so that looking ahead, if you have 10 robots working over the course of a year, do you need to prepare for some massive cloud storage investment?
Yeah, so that's actually a really good question. And obviously, the classic answer is it depends. But the way I think of maybe let's ground this in a little bit more canonical example in like a self-driving car, right? And so what's happening is you instrument the car, you collect the telemetry, you put it on the road, and you update when you see the exceptions, you update the model, and then you re-input the telemetry. And if you do that cycle, a couple billion times, you get a self-driving car that's largely adaptive and can handle virtually any environment, which is probably where we're at today. But the truth is, now I've got 10,000 of these self-driving cars or 20,000 on the road, and they're seeing stuff that you did not see in the original model build. And it may not be as much. They're not seeing as much, but you're going to collect a steady stream of data to make sure that you're getting the full picture all the time so that your actual system is adaptive. It's self-healing. It's becoming autonomous over time. And that's going to require a steady stream of data. I think the same is true for the robot in the house, probably less true. It has less obstacles, but all kinds of systems that want to become autonomous over time have to have that steady stream of data because the real world changes around these systems. The real world is not as controlled as we would like it to be.
Mm-hmm. And the data collected may also be valuable for retraining
Yes.
Yeah. So,
yeah.
But at some point,
so you end up with a fair corpus of data.
Right.
Yeah.
Okay, super. Yeah, it's just, where this is going might be at a scale that many IT enterprises may not be expecting or may be able to accommodate or may not have the budget for right now. And it's good just to understand from a database architecture specific perspective, what this will all entail, because so much focus is usually on the logic and the reasoning and how the autonomy of this can change how we do business, but nothing happens without the data. So that's a critical asset that we need to definitely be prepared to take care of. So one last question, Evan. If you were to advise some executives, managers who oversee the IT architecture for larger companies right now interested in moving toward physical AI, and perhaps also those in senior positions pertaining to the data architecture, database management, database administration, and so on, what would be your top three things for you that you would advise them to focus on?
3. Wow. Okay. I don't know. I want to put them in order because they're going to come top of mind for me.
Sure.
I've been asked this question exactly. I think I'm dealing largely with operational systems. So the term IT doesn't apply in the way that it used to apply. And I think that's true of lots of AI, right? Is the benefit of AI is turning all of this intelligence that we've collected and turning into active data. And that starts looking like operational systems as opposed to what we've typically thought of IT. In the industrial world, they call it OT, operational technology. I think we're moving more to that model because these things are live. And so it's not like we thought of IT in the past. So I think the first thing is to reframe your thinking is, am I building an operational system based on AI? In which case I'm thinking about the whole thing differently. Second thing is the data plane matters in the physical world in a way that it didn't matter before, right? The increasing intensity, the physical AI. And so I see these roles emerging, let's call them data engineering. So in our world, in the operational world, there's a notion of a digital twin, which is you're building a digital version of something that's already physical. And so you build the physical thing first. But very often now, you're going to build the digital thing first now, right? In which you're going to look at whether data pipelines to feed the operational systems you want, because so much is in the AI. So I'd look at these new roles of data engineering, and I would encourage students coming out of school to really look at those roles of how do you build these flowing pipelines of, to feed these art intelligence models to operationalize the data. Because it's not passive. It's not just things we're looking at anymore. It's things that are really happening in a flow state, if you will. So those are two things. Is stop thinking about it like IT and start thinking about like we're building operational technology, hire these data engineering folks. And then, you're not going to get away with a one size fits all. So embrace the idea that you have to be an architect of these systems, that you're just not going to build the kind of systems that your customers or your employees are going to love if you're not going to combine solutions creatively. It's a great time to be creative, right? But it's also, it's complex. It's not, I guess it's always complex, but anyway.
Well, it sounds like it sounds like the complexity might be increasing a bit. But no, that's very insightful. Thank you. So before we conclude, Evan, please tell us more about InfluxData and what you're focusing on there.
So we are, now it's going to sound like I'm just had this lens. We're by far the leading time series database, but there are other good time series databases. We have about 1.5 million people who run InfluxData every day. A lot of people run it in their home to collect everything from temperature measurements, variety of sensors and automation, things like that. And large corporate customers, everybody from Tesla to Siemens to Honeywell to Cisco and IBM and companies like that. And you can find us at influxdata.com. And, our primary issue is when you have these kinds of problems, start with a time series database, either ours or somebody else's. They're relatively easy to use and they're very, very powerful.
And they sound like they will continue to be a core part of this type of architecture moving forward.
I think this business will grow significantly because the amount of data we want to collect, there's an infinite amount of data to be collected in the real world. There's a finite in the digital world. And so the opportunity here is pretty great. So
super. Well, Evan, thank you so much for your time today. It's been very insightful.
Okay. Thank you so much. I really appreciate you taking the time. It's a pleasure to meet you.
Thank you for listening. Follow Thomas on LinkedIn